Well, hello. A number of students have asked if I could prepare some material about preparing for the final thermodynamics exam. And I was thinking, now, how can I do that? And what immediately then came to my mind was my own experience as a student and one of my top professors giving us some advice on things we all know about thermodynamics. I'll say a little bit more about that presentation here shortly, but let's talk about the mechanics of your taking the final exam. And then what I'd like to do is review things that we all know about thermodynamics now that we've been through the thermodynamics course. So let's get started. So here's a pitfall. I don't know exactly what your section is going to be doing, what your professor, what your instructor has said, but here's a pitfall. Perhaps the instructor has said, the final exam is only going to cover the last few topics because you've already been tested on the previous topics. But I see that as a pitfall, okay? So here's a reality. The reality is the final exam will be mostly comprehensive. And I'm going to give some ideas on why am I saying that? Why am I saying that no matter what the instructor says, the exam is going to be mostly comprehensive. So here's what I want to remind you. First, is think about your own problem solving, your own performance on quizzes and tests so far, and what has worked for you. Here's what I hope has worked for you. Every time you read a problem, you start with a sketch. Then you think, now that I've come up with a little sketch, do I have an open system or a closed system? That sketch might be a sketch of the equipment. It might be a PV diagram. It might be a TS diagram, or some combination of those. Then you ask yourself, what's the substance I'm working with? That helps you go through that decision tree of, do I have an ideal gas? Do I have a phase change substance? Three things that are definitely comprehensive that you will be tested on in the final exam. Can you work with the continuity equation, conservation of mass? Can you work with and solve problems using the first law, or conservation of energy? And then finally, I suspect you're going to be asked questions about the second law, in which entropy is nearly always produced. There's only certain few very special cases, reversible, where entropy is not produced. So those are items that I would see of being comprehensive, stuff that you've learned throughout the course that you will be applying on your exam. A little remark about formula sheets. You might be in a section where a formula sheet is provided to you. Well, that's great. Study that formula sheet before you get in there. Maybe you're allowed to create your own formula sheet within certain guidelines. Or you may have an option of using or not using a formula sheet. Well, you've heard me say this before, I hope, that this is your best formula sheet. So I can only highly recommend that you only use a formula sheet as a crutch as you need. Keep formula sheet information to a minimum, because your head, what you've learned and perform in the class, is your best formula sheet moving forward on the exam, your subsequent classes in ME, and then your practice as an engineer. Just some basics about test taking, and particularly the final exam. Read each problem first. That can help you plan your time. Okay. Of course, you're going to take a clock in with you, some type of clock. Okay. Start with a sketch and show your work. Okay. Start each problem on a new page of paper. That's a courtesy to the person evaluating your performance on the test. Okay. I can't tell you how many tests I've reviewed, and it just drives me nuts when a student starts a new problem on the same page as the previous problem work. So I suspect that's true for most folks that grade tests and exams and quizzes. Show your work. Work down the page. That's a courtesy, but also it helps you maximize the partial credit. Showing your work, writing down what you're doing, maximizes your partial credit. Let's see. Do you have an open system or a closed system problem? Write that down. Okay, that's going to give you something. Write down the governing equations that apply. Strike out things that do not apply. Maybe you have a rigid closed system vessel. It's heated. There's no work. Show that, strike out W. It's going to buy you something. Okay. And then finally, the last step is work on numerical evaluations. I can't tell how many students get bogged down and waste time on numerical evaluations when they should be writing down the governing equations, the fundamentals first. Another little reminder that I've had, I think, in a previous video, quote from Seneca from over 1,000 years ago. Luck is a matter of preparation met by opportunity. I couldn't have found that to be more true. All of us feel like we're either lucky or we're unlucky, but we tend to be more lucky when we meet luck or bad luck with preparation. So here's my little formula. You need to know the material, okay, and then perform well by way of practice. And that's what's going to buy you a good grade. And now I'm going to introduce things we all know about thermodynamics. This is one of my favorite presentations. And I can't say that it's an original thought, because my professor, I had Dr. Jones, he was the department head of mechanical engineering at the time, in 1974 in one of my final undergraduate thermodynamics classes. And he was able to do this presentation on the chalkboard with chalk in a matter of a few minutes with no notes at all. He knew this material backwards and forwards, and he wanted to give us every opportunity to communicate, this is what I think you know about thermodynamics now that you've been through the course. Okay. Dr. Jones was an inspiring individual. He had a major impact on my engineering career and also my life in general, on giving us life lessons, all of us students giving us life lessons on the way to live, the way to behave, and the way to serve as an engineer. So this presentation is in honor and memory of Dr. J.B. Jones. Dr. Jones started off with definitions. Now, he wouldn't write all these words. He would basically write the key words on the chalkboard. First, do you have an open system or a closed system? That's a definition, right? Back in the day, we called an open system a control volume and a closed system a system. So I've reversed these labels here. Sorry about that. But open system is a control volume. System, also known as closed system. Properties, you know about intensive and extensive properties. We don't need to go in detail. You know that. You know the difference between an intensive property and an extensive property. You know about temperatures, both in English and SI, and you're now very familiar with immediately transforming degrees C or degrees F into absolute temperatures. Okay. Pressure is an intensive property, and you're very familiar with the units. Okay. And you're familiar with canceling units out as you need in your problem solving. Specific volume is an intensive property, whereas volume, capital V, is an extensive property. So you know the difference between big V and little v. You've got a lot of experience now working with those two. How about density? Oh, is that another definition? No. Density is simply the reciprocal of specific volume. It's also an intensive property. Moving along, more definitions. Internal energy. Now, Capital U, that's internal energy, is an extensive property. And remember that for a closed system, U over little m, U over the mass of a system, is the specific internal energy. Enthalpy, H, remember the definition of H is U plus PV. Been a number of tricky problems where you've had to remember the definition of enthalpy, where you've had a PV term to worry about. We engineers call H, which I think technically is the specific enthalpy, we just call it the enthalpy as a shortcut. Remember that the state of a substance is defined by two independent properties. So a set of properties, two of them at a minimum, defines the state. Remember, in the second week of class, we talked about the difference between work and power. Let's see, work. Work is the act of moving a force through a distance, the integral of f dx. And in the textbook, you just have capital W. Remember, if you've worked with me, remember, I always write W out. That's one of my first thermo professors drilled that into our heads. Don't just write W, write W out. Work out is positive. That's work done by a system. If work is done on a system, then W out is a negative number. Okay? For open systems, remember, for open systems, we're working at some rate. Things are flowing in and out of a system for an open system. And so we have the idea of power. W dot out is power, the rate at which work is done. Continuing on definitions, but we're going to get through the definitions here in just a second. In the second week of class, we talked about heat transfer. Remember, that's a boundary phenomenon, and it only occurs because heat on its own only flows from hot to cold. On its own, heat only flows from a high temperature or a low temperature. Okay? And remember, the textbook just has Q, capital Q. If you're working with me, I always write Q sub n, Qn. That's a positive number when heat is added to the system. So when heat is rejected from the system, Qn is negative. Qn is less than 0 when heat is rejected. Remember the jargon, adiabatic process. It is my bet that you're going to have a phrase, adiabatic process, on the exam. You had better know that an adiabatic process means the system is fully insulated and there is no heat transfer. Q is equal to 0. Let's see, about the third or fourth week of class, you got good at interpolation. So remember that this is a little screenshot of my tried and true interpolation scheme, okay, that I've used thousands and thousands of times. And so it's my hope that you're good at interpolating as you're looking up properties in the back of the book. We know some fundamentals of definitions of specific heat. Now, if you are graduate school bound, you're going to need to know these by heart. It is possible that you will not be asked on the exam, what's the fundamental definition of CV and CP, but this is where our starting point was. These partial derivatives were our starting point for dealing with CP and CV for ideal gases. Let's see, one more slide on definitions near the end of the semester. So I wanted to put this in to be absolutely sure for those of you where the instructor said, no, we're only going to be covering what's the last part of the material. Let's be sure you remember these fundamental definitions. Partial pressure of an ideal gas mixture. Okay, partial pressure, that came from Dalton's model. So remember that the partial pressure is the mole fraction times the measured pressure of the system. Mole fraction times measured pressure of the system is the partial pressure of each constituent. The humidity ratio, that's omega, that's not W. Omega, Greek letter omega, defined as the mass of vapor in the mixture divided by the mass of dry air. In atmospheric air, the air that we breathe, okay? Hopefully in class you derived another expression for omega. The humidity ratio is 0.622. That's the ratio of molecular weights of vapor, H2O, divided by dry air. Okay, 622 times partial pressure of the vapor divided by the partial pressure of the dry air, which is P of the system minus P of the vapor. Another important definition, relative humidity. Remember how relative humidity, Greek letter phi, is defined. Phi, relative humidity. It's a ratio of partial pressures. It's the partial pressure of the vapor divided by something you look up in the steam tables, PG, the saturation pressure of H2O at the temperature of the mixture. That's the definition of relative humidity that you have a pretty good physical feel for. Finally, the dew point temperature of the dew point is the saturation temperature at the partial pressure of the vapor. It's basically a lookup value. Once you've figured out what is the partial pressure of the vapor, go to your temperature table, look up T sub G against whatever the pressure of the vapor is. That's the dew point temperature. That's where in an atmospheric air, when that atmospheric air cools down enough, that's where dew forms on the grass. That's the dew point temperature. Okay, so now we're getting into problem solving. That was sort of a long list of definitions that you've covered throughout the whole semester that Dr. Jones thinks we all know this, okay, in our heads. Okay. All right. We read a problem and we start planning our work. And so the first thing we do after we've drawn a sketch is either heat or work found at the system boundary. And then we go through, do we have a closed system, or do we have an open system, a control volume? Closed system, Qn greater than 0 means heat flows into the system. For a control volume, remember there's no Q for an open system, but we have used little qn, which is q dot divided by m dot, the rate of heat transfer divided by the mass flow rate, and that would be for one inlet and one outlet, m dot. Same flow in, same flow out. How about work at a system boundary? Can we see work at a system boundary? Is it a piston cylinder? Is it moving? Okay. If the piston's moving, you've got work involved. Work out greater than 0, that's positive. Okay. Remember, for a quasi-equilibrium process, now as we went through the weeks, we learned that a quasi-equilibrium process is also called a reversible process. A reversible process. And we have, for a closed system, the work out, work from say 1 to 2, is the integral of PdV. Boy, that is important to have in your head or on your formula sheet, and you know what that refers to. It doesn't refer to everything. It refers to closed systems undergoing a reversible process. Let's jump over to control volume, to open system. Now, we don't have work, capital W, we have little w out. We use that a lot in cycle analysis. What does that mean? What is little w out? It's W dot over M dot. Okay. The power divided by the mass flow rate. And then for a reversible open system, steady state, steady flow, reversible process. So for a reversible process, steady state, steady flow, no change in kinetic or potential energy, the reversible work, W dot over M dot, equals minus the integral of VdP, minus the integral of VdP. Where did we use this in practical applications? Where did we use this for practical applications? We used this fundamental for calculating W dot over M dot for a pump where V was a constant. Okay. That's going to be valuable to remember in preparation for the exam. Go back and do some cycle analysis, Rankine cycle analysis, to refresh your memory on using this fundamental. Moving into the continuity equation or conservation of mass. Let's look at a system, a closed system. What's a statement of continuity for a closed system? Well, the mass is fixed. So M1 equals M2 for my little sketch. The mass is fixed. That's a statement of continuity. How about a control volume? Well, what do you expect is going to be on the exam? Don't you expect that you're going to have a steady state, steady flow problem and not a transient flow problem? I think so. Okay. You might have steady state, steady flow, one inlet and one outlet. So in my little example, I've shown a turbine. There's some kind of substance going into and out of a turbine. W dot power is produced. I'm showing W dot, okay? So for one inlet and one outlet, steady state, steady flow, continuity equation is the mass flowing in exactly equals the mass flowing out. That's easy to remember. What if you have a problem that's multiple inlets and multiple outlets? You've had a few of those in the semester. Well, continuity equation, conservation of mass, sum of the mass flow rates in equals the sum of the mass flow rates out. Now, let's say you get a really tricky, I don't expect it, but let's say you get a really tricky problem on the exam where things are changing in time. Things are different at lunchtime than they are at breakfast time. Well, continuity equation says the right-hand side, dm dt of the control volume. That's the rate of change of mass of inside the control volume equals the sum of the m dots in minus the sum of the m dots out. That's something you know, but I don't expect it's going to be on your exam. One thing that high probability, calculating the mass flow rate when you're given the volumetric flow rate. So this one is critical for you to remember. M dot, the mass flow rate. M dot equals rho A V. Let's say at the inlet or at the outlet, depending on what's given. And remember your textbook, the textbook might say, not say M dot equals rho AV. The textbook might say M dot equals AV divided by little v. That's identical to what we're saying here. Remember, little v is the reciprocal of density. M dot equals rho AV. That's an important thing to get in your mind. Moving on to the first law. So we're problem solving here. You've read the problem on your exam. Okay. You've done a sketch. You've decided on your substance. Do I have an open system or closed system? I'm asked for the heat transfer. If you're asked for the heat transfer, you're going to need to use the first law, probably. Okay. So what's the first law for a closed system? First, you should know this off the top of your head. Q dot in minus W dot out equals the change in internal energy, delta U, plus change in kinetic energy, plus change in potential energy, plus change in other energies that we really didn't address in the class. The statement of the first law for a closed system. Let's move on. Here's a little special case, a closed system operating in a cycle. And so remember, when you see the word cycle in a problem, you immediately draw a sketch, like a schematic sketch like this, and you refresh your memory that for any system undergoing a cycle, QH minus QL equals W net for one single cycle, or if it's operating at a steady rate, Q dot H minus Q dot L is W dot net. All right. Control volume or open system. Let's say first law for an open system. Okay. So you're on the right-hand side of the slide. Most general application. Now, it's a number of instructors start with this expression of the first law. That is great. I think that's terrific to start with this. But let's look at the terms. Q dot in minus W dot out on the left-hand side. That's the way I was taught. Q dot in, the boundary phenomena go on the left-hand side of the equal sign. On the right-hand side of the equal sign go a lot of the other terms. dE dt of the control volume. What does that mean? That means that in the transient process, and when something is happening that depends on time, when lunchtime is different than breakfast time, dE, that means the rate of energy contained in the control volume is changing with time. I will be surprised if you have a question like this on the exam. Plus a couple other terms, the sum of the m dots leaving, H leaving, kinetic energy leaving, potential energy leaving, minus the sum of the m dot entering, enthalpy in, kinetic energy in, potential energy in. So that's the most general statement of the first law. Dr. Jones expected us to know that in our heads. I'll have to admit that as an undergraduate, I didn't have that in my head. Okay. Steady state, steady flow. I had that in my head. Okay. Remember, the sum of the m dot ins equals the sum of the m dot outs for steady state, steady flow. One inlet and one outlet, there's only one m dot. Okay. For one inlet, one outlet, steady state, steady flow, open system. Q dot in minus W dot out equals M dot, it's just one of them, times enthalpy change, H out minus H in, kinetic energy change, V squared over 2 out minus V squared over 2 in, potential energy change, out minus in. Now, in our cycle analysis, what we did was we divided this whole equation by M dot. To get little q in minus little w out simply equals all these terms. And so if you're preparing a formula sheet, remember, you don't need to write both of these down. You have to remember, you should write this one down for steady state, steady flow, one in, one out. You write those words down and go from there. Okay, so first law of thermodynamics for systems operating in a cycle, it's important to devote a slide to that. And Dr. Jones did that on the board as well, recognizing the difference between a heat engine, okay, that's a power plant, or a refrigerator or a heat pump. Both of these are systems operating steadily in a cycle. Just notice how the arrows are reversed. So we can transfer heat from low to hot. We can do that at the expense of investing power. So this is not a violation of the second law. It's perfectly valid under certain conditions. And you remember those certain conditions related to the Carnot cycle. And there's also certain conditions where we can operate a power plant that are limited by the Carnot cycle. Okay, second law of thermodynamics. We started in chapter 5 with this basic definition of entropy change. Okay, I'm going to have to admit that as an undergraduate, I did not have this derivative or differential equation memorized. I didn't have it. Okay. However, what that led to was a very important relationship for ideal gas with constant specific heat. Cp is constant, K is constant, and an isentropic process. What does isentropic mean? Reversible adiabatic. You got to have that in your head. Just writing that down on the formula sheet is not going to help you. You have to have this in your head. Isentropic means reversible adiabatic, and the good result is PV to the K is constant. What does that mean? P1 V1 to the K equals P2 V2 to the K. And then you can derive the rest. Okay, now production of entropy. Entropy production, Greek letter sigma. Remember, it's sigma for a system. It's sigma dot for an open system. Remember, closed system, control volume, open system. Okay, so for a closed system, the entropy production is greater than 0. Okay, what's that definition? This is one that you definitely want to get on a formula sheet or commit to memory. And I'm going to have to admit that as an undergraduate, I did not have this exact approach committed to memory. Entropy production, sigma, equals minus the integral over the whole system boundary of del Q over T, that's entropy transfer, plus capital S2 minus capital S1. That's the entropy change of the closed system. That would be M times little s2 minus little s1. Okay. Over here, entropy production rate, sigma dot. Well, if you've got the closed system, you've got the open system similarity. So sigma dot is equal to minus the sum of all the heat transfer rates in over the reservoir temperatures that they're coming from are going to, plus m dot leaving, little s leaving, minus the sum of all the m dot in, little s in. And so then remember, a statement of the second law, it says when sigma is greater than 0, the proposed process is possible and irreversible. If sigma exactly equals 0, the proposed process is possible and reversible. In other words, that would be kind of like a Carnot cycle. It would have the performance just like a Carnot cycle. And then when sigma, if you calculate it and it's less than 0, whoever's proposing a process to you where you calculate sigma less than 0, you can come back and say, that is impossible. That can't be. It would violate the second law. It is my hope that you're good at thermal efficiency and coefficients of performance for these three important categories of equipment: power cycles, thermal efficiency. Notice how, let's look at all three of these measures of performance and see what they have in common without dissecting the formulas. You can go back and refresh your memory on all these formulas, but my claim is that you can figure the formulas out on your own without writing them down, as long as you use some common sense to recognize that eta, beta for a refrigerator, and gamma for a heat pump, all of them equal the energy sought over the energy that costs. And for those of you who've joined me online, boy, I beat the heck out of that when we were talking about these cycle problems. How do we figure out, using Common Sense 101, what's the energy sought for a cycle and what's the energy that costs? So we don't need to spend more time on this slide. You may want to study on it, because if your instructor said, we're going to have a comprehensive exam, the chances are awfully good you're going to be giving some type of cycle problem that might be simple. How many of us read a problem and you pray for an ideal gas? I got to tell you, when I was an undergraduate, I was praying for the ideal gas with constant specific heat. So if you've got an ideal gas problem, this is the stuff you know, and this can help you quickly solve problems. For a closed system, well, for all ideal gases, R is R bar over the molecular weight. You've got that. For a closed system, these are three identical statements of the ideal gas equation of state. PV equals MRT. You can derive the others. For an open system or control volume, notice there's no mass. That's because you've got mass flowing into and out of a control volume. So P times little v equals RT. Remember, there's a jingle for a closed system. For fixed mass, P1V1 over T1 equals P2V2 over T2. Boy, I used the heck out of that as an undergraduate when I had ideal gas problems, closed systems. For any ideal gas, here is the expression for internal energy change and enthalpy change. Now, you can also derive and remember that C sub P minus C sub V equals R for all ideal gases. Cp minus Cv equals R, well, that's a constant. All ideal gases, whether specific heat is variable or constant, the difference between Cp and Cv is always R. Now, what were we praying for when I was a student? Your undergraduate students, well, you're praying for constant specific heat, I hope. And so it becomes easy to calculate U2 minus U1 is Cv times delta T, and delta H is Cp times delta T. Ideal gas, constant specific heat. Okay, so when do I use table A22? You only use table A22 for the ideal gas air, and if you do not have constant specific heat. In other words, you have variable specific heat. Okay, so if you're not given any direction in the problem and you have an air problem, you are certainly entitled to use table A22. If it's given constant specific heat, you cannot use table A22. Now, I threw this slide in. I would be very surprised if you have a question about the compressibility factor Z for an ideal gas, because it was such a small part of the entire semester. So as a reminder, well, what is Z? Numerically, Z turns out to be some number greater than 0 and less than about 1.2. And also recognize that Z it's called the generalized compressibility factor. And look at visually, do you see that it's sort of like a adjustment factor for the ideal gas equation of state, recognizing some variance of various gases away from the ideal gas model. Okay, so that's enough I'll say about. So you remember this, you remember enough to maybe if someone springs something on you, remember you've got TR and PR and you got to jump through some graphical hoops to determine Z. We are moving along. We're getting close to being masters at thermodynamics. TDS equations. If you are graduate school bound, you must, or you will need to know these two differential equations by heart. I'm going to have to admit that as an undergraduate, I didn't exactly know those by heart. At the master's level, I quickly learned to get them by heart. Okay. So, but if you have them, you can derive for any ideal gas this set of differential equations. And what do they lead to? Well, what they lead to is expressions for change in little s. Little s2 minus little s1 equals this expression. Okay. And so if you don't have, and so recognize for constant specific heat, you can derive these simple relationships for little s2 minus little s1. Okay. So another outcropping of these TDS equations is the fact that PV to the K equals constant for an ideal gas with constant specific heat undergoing an isentropic, reversible adiabatic process. So you can start with this, PV to the K is constant, and as an engineer, you can derive T2 over T1 equals P2 over P1 to the power of K minus 1 over K. So you can derive that from the TDS equations. How many times early in the semester did you draw a pressure volume diagram with a vapor dome of substances that could change phase? And you got very good at identifying, depending on where your state is at, under the dome or to the right of the dome or to the left of the dome, what phase that substance was in. Okay, so we're not going to dwell on that, but that's a good thing to remember. PV diagram, what's the phase? How do I solve problems? And one of the big problem solvers was X, quality. So whenever your state is underneath the vapor dome, you're dealing with X, the quality. And this slide's going to remind you, how do I calculate quality? How did I calculate quality? It's a ratio. It's a ratio of where you're at divided by the total distance, let's say delta V from VG to VF, VG minus VF. That's the denominator part of your quality expression. Then, once we got into chapter 5 and introduced entropy, we had a vapor dome on the TS diagram for phase change substances. So notice a little different look. Let me go back. Look at this. Oops. Very steep left-hand side of the dome on the PV diagram. Very symmetrical looking on a TS diagram, but it's the same idea, same idea. You've got, when you're under the dome, you're dealing with quality X. When you're to the right of the dome, you're in the superheated vapor phase. When you're to the left of the dome, compressed liquid phase. When you're on the dome, you're either saturated liquid or saturated vapor. And so that would be a review of from the midpoint of the class on up to now. That is things we all know about thermodynamics. Wow. Imagine what you've learned in this class over the last number of weeks, 15 weeks or something like that. A lot. And you've gotten good at problem solving because you've worked a lot of homework problems, you've worked on quiz problems, and you've gotten better and better at problem solving. You've gotten better and better at showing your solutions. And so now you've got the final exam ahead of you. I wish all of you all the best for good performance. I'd say good luck, and do your best to prepare for the exam. You've been preparing for the exam the whole semester. So do a little review, go back and maybe download these static slides. Amazingly, so I can assure you that Dr. Jones went through this on the board in a matter of maybe 10 to 15 minutes at most. It was a 50-minute class. And so he was able to breeze through that. Imagine us students with pencil and paper in our spiral notebooks, busily copying down everything he was writing on the board, and we'd go back and study and refresh our memories. But because we did not have formula sheets back then. Now, you've got it harder. You're covering more material in a shorter amount of time. So I don't want to throw cold water on the formula sheet idea. But I want to thank all of the instructors in Thermo. Every one of the instructors that I've had contact with, that's all of them, have done a good job. They've done a great job of talking about and communicating those things that are important to them. They've done a good job of providing you with the fundamentals, and they've done a good job of showing you how to solve engineering problems related to thermal systems. So best of luck to all of you. I hope you do well, and best of luck beyond this class and the rest of your engineering courses, and best of luck as you begin an engineering career or graduate school.